There's 2 to 4 of you that haven't responded to me yet since for like the past month, so I'm just bringing it up. Over here, this is my the clicker software that gets your answers. And right here on the left, under unassigned devices, 2 or 3 of those I've emailed twice the whole class asking who had those. Those unassigned devices are still participating. Some of you are coming to class and using these devices. 2 others have one or 2 have shown up. Thus, if any of you are those 4 unassigned devices, you're not going to get any credit for any of this until you tell me that's your device because you never registered properly or told me. I hate to say it, but look, if that's your unassigned number, is this your unassigned device? Oh, I know. I assigned yours. I mean, you're up here. Let's see. Ron. You're there, and your device is over here. I saw it. You're getting scores under your name, but these 4 are not. So I just thought I'd ask the next couple classes because you can see on the right here. Last time we used it, one of them worked. The other time, the other 3. This person did it here. So there's 4 of you coming and still participating. But I don't know. Is that anybody that's here today? I'll email this out again to the class because I'm sure obviously they're not here. But okay, it's worth a shot. Yes? Then email me your name and that ID number, please, so I can attach it to you.
Oh, the points over there, do they represent anything at all? I mean, 7 and 8 and...
That's how many you responded to, yeah. Yeah, every time you respond, you get a point. If you don't respond, you don't. If you're not here, you don't, yeah. Any other of those devices that's here today? So yeah, just email me with that device number and your name. Tell me what's going on, and I'll hook you up, and then all of those will get under you. Are you listening to me? Then you'll get credit for those. Okay, there was another question or concern I had. Mel, are you here today? I don't see her. And who's the other one? Is Mark Nielsen here? Okay, we still have some people that actually aren't registered. Okay. And just within the past week, I got lots of questions, which I don't mind. But they were all about the same thing, which you all have access to. So a friendly reminder, in case you want to be more proactive. There's a calendar on WebAssign, and under Resources, I printed one from the get-go that has what we're covering when. Like today we're on Chapter 13, when the tests are, when the homework assignments are due. It's posted from the get-go. Also, when assignments become available, it's generally as soon as we start the topic, or right after the last one. Thus, you know right from then when it's due. Well, you already know, but it's there more in your face. And you can start working on it from then. And the superhero. It's time to make sure you're thinking about it. It is not due until April 2nd. Seems like a long time away. That's the final. You can turn it into me anytime up until then. After that, forget it. But so March, the next month that's coming up, is some of the transitions, things you need to take care of to get total points. So if you haven't given this any thought, I encourage you to at this point. The 3 main ones we just did are, this is from posted on WebAssign under Resources. But here, these other requirements, the red dates there. So the bottom one's when it's due, but there's 2 other deadlines to help you improve your paper, and frankly, so hopefully you don't do it the night before, and it'll be better quality for me and less stress for you. The first one, you must inform me of your superhero's name, power, and a list of at least the majority of your sources. I realize you might find other ones. But I just want some proof that you got something in mind and you're thinking about it, it's not going to be a whim the last minute. And you can tell me, actually email would be preferable. That way I have it in writing and I won't forget to mark you down. Does that make sense? Easy enough? So basically you need to come up with something by March 7th. That's in a couple weeks. If for some reason you really want to change it after that, talk to me. I won't, if you're hating that or you start researching it more and that's not going to work, we'll see. But this is to get you going and thinking. And then the next one is March 26th, where I'd like you to at least have a rough draft. So you've at least addressed everything and written a paper. It might be the wrong length, you might not like it, blah, 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 but it's a rough draft. You know what a rough draft is. And have it peer reviewed. So it's as easy as, I know you two are friends, so logic is you might review hers and she reviews yours, but it doesn't have to be in this class either, but I think it'd be more useful in this class. Because, say she has a paper and Emily reviews it, she'll make constructive criticisms and comments on it that'll help Lee, and then they'll both sign it, come to me and show me, and I mark it off and you get credit. It's good because you get feedback, but it's also good you get to see what somebody else is doing to give you ideas like, oh, I never thought of that, maybe I should do something like that. Or you can feel better. Oh, mine's, I think mine's a lot better than theirs. They need more help. Well, then you can help them. Anyway, that's the point of that. Any questions on this or the rest of it? Yeah.
For the peer review, we give you a physical printed copy of.
Yeah, because you'll have to print it out for your, so your peer can make comments. I guess if you prefer to do it digitally, like in Word, where they can insert comments or something, then send me that digital file. I just need to see the comments that they were useful and done. But that your peer person has to sign the paper. I still need them proof, so you're not faking comments and saying and attribute it to somebody else. So I mean, your peer reviewer can lie to me, but then if I catch it, you're both in trouble. Any other questions? I want you to have fun with it. I really do. The main purpose of this is to get you to try to explain stuff. Remember me at the beginning of class that if you're having trouble with concepts, when you actually try to verbalize it to someone else or write it down, teach them, it kind of straightens out your thoughts or you realize where your holes are at. So pick something that interests you and we'll improve. Yes?
Could we present a visual concept of our superhero as well?
Visual concept.
Like a drawing or
Oh, I would love a drawing. Yeah. Yeah, the example I gave, I actually went to a website where you can design your own superhero and had it digitally make a cool picture with a logo. But if you want, you can draw it too. Yeah, that's fun. I would love pictures, cool names. It makes it more interesting to read. I don't want it to be drudgery. Oh, it's Newton's third law man. Okay, that works, but it's not as exciting. So.
You said you want a majority of the sources. What?
I want proof that you've gone out there and have looked where you can find info. Say that again?
Aren't we making up our own secret?
Yes, but you have to justify it with physics. So these concepts that you're justifying. It could be the textbook. It can be me. It can, sources. They can be interviews, personal contacts, websites, textbooks, videos. Just give credit where you learned something. If you went and studied more about refraction of light, well, where'd you learn that info? Again, it doesn't have to be something we've covered in this class because we can't cover everything.
what format do you want the sources in?
I just said it doesn't matter.
Okay.
You mean the works cited format?
Yeah, like MI.
I've always disliked strict formatting. So my message to you is give me enough info that I could go right to where you're at and find exactly what you were looking at. Whatever order, as long as it's neat and tidy. But you need a period here and 2 spaces, a semicolon. No, put this first. Whatever. As long as the info's there.
Could you go over how you're going to be grading it, the grading rubric for it?
It's all on there. So what's your question?
Just go over what you're looking for.
No, because it's all right here. If you have questions because you don't understand what it means, yes, but it's right there. So it's 55 points. I give you 5 points for this deadline requirement stuff, 5 points for spelling and grammar and English. I want to be able to read it. And then here's the other breakdown for the science part. So I'm happy to explain that more, but just that's why it's there for you the whole time. If it's confusing, let me know. I'm happy to elaborate, but that's why it's there for you. Basically, you come up with a superpower based on a fundamental principle. You need to define it so I understand it. I expect this thing to be full of physics. Justify to me why this works or why it doesn't work. Just show me that you understand the physics. Be logical. And then you're describing the superpower and how they'd use it, the origins, how they came up with it, and the viability. Because every superhero generally has some weakness or something that doesn't work but can. This works, this doesn't. When he comes up against this, no problem. But when he comes up against this, maybe. That's the idea behind the fourth one. Yes?
In the paper, do you want, like, say, the person use like a past person or second person, or do you need to be that in the third person?
You can include as many people as you want, but there's one superhero. And he should have one main superpower. I don't want you focusing on 10 and diluting it. Narrow it down very specifically. If you have questions, if it's not specific enough, let me know. Or there's a team duo and there's similar powers, talk to me because it can probably work then, as long as you're not having to spread yourself too thin. But I'll know that when you meet deadline number 1 and we can discuss it. If you come up with your name and person.
I think he means like, do you want it in first person, second person, or third?
Oh, you meant the voice of the paper? Oh, whether it's passive or active, first person, third person, I do not care. Whatever's interesting and fun to you. The more enjoyable it is for me to read, I'll obviously like it better. But yeah, some people have turned it into like a story, like I'm watching a movie. And others have been very documentary-like. Whatever you're comfortable with. Thank you, Emily. Sorry. Okay. Cool. Good. Let's do a clicker question. So let me connect here. All right, there's your info, and I'll set it up. These are some vases. Is that? Oh, you know what? I'm ahead of myself. Apologize. That's going to be the first question. We'll come back to that. You guys are ready for it. We will do it. So, we get to start liquids today, and next will be gases, so chapter 13 and 14. They're both fluids, things that flow, liquids and gases, so I'll often refer to them as fluids. When I say fluids, I mean either or, liquids or gases. I also want to mention that, if you've noticed, I skipped over the circular motion stuff in the book. For those of you that are interested, and I know some of you might continue in physics, here's your brief 2-minute primer. It's the same stuff. That's why I'm skipping it, so we can expose you to other cool physics phenomena of the world. But it still involves velocity, position, acceleration, momentum, collisions, inertia, energy. All of that is in circular motion. But instead of going in a straight line, linear, they go in a circle. But everything I've taught you is the same, essentially. So instead of having change of position this way, it's an angular position because it goes around so many revolutions or so many degrees. velocity. Instead of calling it velocity, distance over time, it's angle or revolutions over time. It's called angular or rotational velocity. And you know the difference because if you're on a merry-go-round on a play park, do you guys know what that is? If you're in the middle, center of it, it doesn't feel like you're going as fast, right? But if you move out to the edge, now it feels like you're moving fast. Relative to the ground, reference frames, you're in motion with respect to the ground. Yeah, you have a big velocity. You're used to that one. Are you with me? You're moving fast with respect to the ground. But whether you stand on the outside or the center, or just outside the center, both of those move around in the same time. Do you see that? Since the one on the outside has further to go, they travel faster, has a higher velocity. But they both have the same angular velocity because they displace the same angular position in the same amount of time. That's the only difference between this stuff. And then there's angular acceleration. We had inertia, resistance to change of motion, of changing its velocity. Angular momentum is the same thing, a resistance to spinning faster or slower. So, there you go. I just summed up 2 chapters. Liquids. We've dealt a lot with forces. And with solids, liquids, and gases, it makes sense with solids. That's what we've been dealing with a lot. That exerts a force on the table. But when you start looking microscopically, or if you have a liquid, which particle am I looking at? Yeah, this exerts a force on the table, but it also exerts a force on the edge of the bottle and on this side. There's forces everywhere in there because all those little particles. Which one do you pick? So basically, they come up. No, they didn't come up with. But pressure helps us define that. So instead of picking one and adding up all these individual forces, we kind of do it in bulk, in mass. And we use pressure. So we define pressure as a force over an area. So this is area, and you know force. The units work out to be, what's the unit for force? Good job. Area? Good, meter squared, because meters for length, and it's an area. So there you go, a Newton meter squared is what it is. And yes, that one happens enough that they gave that a name too. That's called a Pascal. Scientist's last name, the featured scientist in this chapter at the beginning, a Pascal. And you know this. It makes sense for most people. I should probably do this up here. If I do it up here, maybe you can see better. Little Dixie cups. Put this on here. What will happen if I stand on it? How much force does each cup have to support of my weight? The fourth. There's 4 of them. So each one only has to support a quarter of my weight. What, you think it'll do it? Careful. No. They're Dixie cups. Okay. So the idea is, we had my weight spread over just the area of 4 cups. Each cup didn't have to support my whole weight, only a fourth, but that wasn't enough. So let's add more. I'll do an array of 5 by 4. So that'll be 20. So each one only has to support a 20th of my weight. Do you think they can do that? Or am I going to need more? We'll start with this, shall we? Who thinks it's going to crush? Oh, we got believers? Want a drum roll? Hey, what do you know? Even jiggle a little bit, right? So yeah, I can do that. So let me center myself. What if I do 1 foot? What will happen? Does the weight change? No, I'm not changing the force or the weight. So if this was a bathroom scale and I stand on 1 foot, it's going to read the same weight. But what happens to the pressure? By how much? It doubles, yeah, because I've decreased the area. I got 2 feet. If I do 1 foot, it'll be half the area on the board. So there'll be twice the pressure on the board. Now the board spreads that back out, and I'm not changing the area the cups see. So it still doesn't fall because the board's spreading it back out. I just don't want to fall. There we go. How much does it take? Well, pretty good. So that's the idea behind pressure. And I love any chance I get to stand on the table. So I heard him crinkle a little, but we're good. Now, how many of you like to snowboard? Thought there'd be more in Utah, especially with the Olympics. Skiing, snowshoeing. All of those spread your weight over a larger area, so it decreases the pressure, and you're less likely to sink into the snow when you have those on. And it's the same idea, right? Would you rather have me step on you with these shoes, right on your chest, or put on some high heel stilettos and step on you? That'd be scary for a couple reasons, but you want these shoes because it spreads it out. Snowcats do that. They got big feet. Why? Less pressure on the snow. The cups can handle that. So snow, you know what I mean. Now, you take a bunch of fluid and it's spread over an area. So like this guy, he has a weight. It weighs so much and it pushes on the bottom of the beaker. And so you can put in his weight, mg, all the mass of the water times G, over that area. And you get the pressure exerted at the bottom. Same with a block. If we do it this way, this weighs 11.5 newtons. So when I spread it over this area, I calculated it was 639 pascals. 639 is the pressure. But when you do it this way, it's 1,420. 1,420, because the area is less. And that's the pressure at the bottom here on the table. How do you figure out pressure, though, on the sides of the wall? Is the fluid pushing against the beaker sideways? Most people, that's intuitive. If it's not, what if all of a sudden we remove this wall? If we could do that, what would the water do? Yeah, it's trying to push that way. So yeah, there's pressure in all directions in the fluid. So just coming up with its mass times gravity doesn't always work. So we have another concept that helps, and that's density. And I told my daughter I'd share this one. I just love density. I just love it. This is what her teacher taught her. Because density is mass over volume. D for density. Density is mass over volume. Big V, not velocity. It's that ratio. So you can't just think of how much substance there is anymore. It's how much space it takes up also is density. I hope this is all familiar to you by now. But yeah, I just love it. That's how you can remember. You won't even need a cheat sheet. I'm getting a few smiles. I have to tell her you guys didn't react as well as her class did. Okay. So with that, watch what you can do. Make sure I do it right for you. Pressure is force over area. So if you take the weight over that area, that works for some things, but not like sideways and things. So what we do is we replace the mass in terms of density. What would that be? What is the mass? It's density times volume. So we'll just put that in here. Then, some fun rearranging. I'm going to volume. You remember your volume? If you have like the bottom of a cylinder, this bottom has a certain area. How do you find the volume of the whole thing? You take that area and you multiply it by the height. Do you remember that? That's volume. So if we put that in here, then the areas cancel and you're left with density. So I'll often be referring to this formula. That, and that are our guides to thinking for most of the next two chapters. We got pressure in general. This is the same formula, just rewritten so that we can deal with fluids easier with their density. Instead of how much they're made up of, it's how much there is versus how much space it takes up. So what this tells us is, now the clicker question. See if you can, before I tell you, apply this to this. We have 4 vases here. I have a valve here that's closed. So I can pour water in the top one. This one on your left. It's just blue water so you can see it better. That's probably enough. What I'm going to do is open this valve and let this water flow. It's connected internally in here. It's open here, here, and here. And so the water will flow. What will happen? Will the water flow into here? Will it flow up these? If it does flow up those, will they go to the same height, different heights? Will this one remain the highest? Will they all end up the same? This one's skinnier. Will it be higher? That's our clicker question. So let me pull that back up. So there, if you didn't log in, guess I can go ahead and open it. So in which vase will the water be highest when I do that? A, B, C, D, or E, they'll all be the same. Might remain highest in D, where it started. I want to see what you guys think. Your clue is those formulas are going to guide us to understanding this. Oh. Bummer. Okay. Darn clickers. It doesn't have an E?
Yeah.
But it says not an option because you tried.
Oh, I bet I know why. It's okay. It should be. My default is for 4. Yeah. Is it AA or AAA? Oh, okay. I'll go get them. Let's just change it. Let's say make option D, they'll all be the same. In other words, you don't get a choice. If you think the one D is the highest, well, you're wrong. D will be they're all the same, okay? AAAs?
Yeah.
And now I know to change the number of options off my default when I have an E. All right, everybody's probably voted, so let me know when you voted, battery man. These are often called in the demo world Pascal's vases, after Blaise Pascal, again the featured scientist in this chapter. Any questions while we're waiting so far? So just a reminder, when you're doing these homeworks, and why not remember density. It's not just how much of something you have. Something can be really heavy, a lot of mass, right? But if it's spread over a really big volume, what's its density? Big or low? Low, yeah. The volume will affect it. So when you're thinking about whether things sink or float, rise or go up, weight doesn't, just because you think it's big, really big, it's not all there is to it. Or it's really heavy. Got to consider the two, the ratio of density. That's why I love density. Did you vote? Okay. Well, I haven't confuddled the masses. You all think about the same thing, so we'll do the experiment. You ready? It's flowing down. It's down in here, and we're not doing anything. Oh, wait, now they're going up. Going. This one's still higher. And now they all went to the same. This one's kind of skinny. Can you see it? So you're right. Tell me why we're all right. Your physics definition. I'm glad your intuition's right, but tell me. Water sinks its own level. Good. And the chapter refers to that. So that's what it's doing. In terms of this, how do we explain it? This tells us why it seeks its own level.
When I read that, what is its own level?
They all come to the same level despite their size and shape. This is another way to do it. I brought this one out. I just filled a hose here.
Before you threw the switch, it had a level.
Yeah, that one was higher. That's where the water level settled. I opened the valve, and it was free to move and flow, but it all came to its own level. One wasn't higher than the other. And this is intuitive to most people. As you can tell, you all got it right too. But see, they're the same level. They're still the same level. They're still the same level. Wait a minute. They're still the same level. They're still... Okay, I got an air bubble. I can raise this up slowly. And look, this is higher than that side, but the level still the same. This is if you read your book, the Romans did a lot of extra work that they didn't need to with their aqueducts. Long story short, a lot of them they didn't understand this principle completely. And so they built these big, beautiful structures to ensure that water could flow from over there to the city where they needed it, but they made sure it was always flowing downhill. It doesn't have to. Look, it can go up and still come back to the same level if it's enclosed like this, connected. But at least they're pretty. They had lots of slave labor, so they didn't have any issues. What's that? Yeah, a lot of extra time, yeah. So this, giving you enough time to think, is to really emphasize that pressure is depth dependent. You should write that down. Pressure depends on the height of the column of fluid above it. This H, see? It's depth dependent. How much water is above it, that point? So over here on this one, the big one, the pressure here is based on how much, the height of this fluid, not the width, not the volume. You can have a dam that's 30 meters high. So the pressure at the bottom of the dams are really thick at the bottom. Have you ever noticed that? I don't know if you have. They're really thick. Why? Because the pressure is greater down there. Pressure increases with depth in a fluid by this formula. And if the pressure is great there, it's spread over an area, it's going to create a force. That pressure down there times the area of the dam is the force, so it has to withstand it. But you can take the same 30-meter dam and it will hold back a lake or the entire ocean if they're 30 meters at the dam. It's the height that matters, not the volume of water behind it. It's the height of the water above it. I'm really trying to emphasize that. So here, the pressure was something here. I released it, and that pressure pushed into here where there wasn't any fluid. Well, look, down here, same height. Same position. So it's going to be the same pressure here as it is here, as it is here, as it is here, and it pushes them to the same height. Or look at it this way. Here's a column of water that high, so it creates a pressure here. This is the same height, so it creates the same pressure. Since there's not a difference in pressure, it's not pushing water one way or the other. So they balance. If this one had a higher pressure right here, what would happen? If the pressure was greater here for some reason, what would happen? This pressure would be pushing on the other ones that are lower and make the other three go higher. But they're not doing that. Water seeks its own level. The pressure's all the same. It's only height dependent.
If you have a dam on a really deep reservoir, and dams tend to be wider at the bottom.
And you know why they're wider at the bottom now?
But when they fail, do they fail at the bottom? Because that's where the most pressure is? Or somewhere where
Are they more likely to fail at the bottom than anywhere else? My gut says yes. I'm not a dam expert. Did I say that? My brother-in-law worked, he's in the Army Corps of Engineers. Hi, Patrick. And he worked one spot where there was a dam, and he'd give us a dam tour. And, of course, we were doing all the dumb jokes. We wanted to go to the dam store, but anyway. So, given the physics, they should. There's a lot more force at the bottom because the pressure's greater, and so it feels more force. And so, yes, they have to withstand it more, and they are more likely to break down there. Now, erosion and weathering up above could have other factors, and that could dominate, and I don't know. But yeah, water towers have a big pressure at the bottom. You see one that's really big? That just means it can hold more water, so you can reach more people. But one that's taller has greater pressure, so you can get a better pressure flow out to the houses or maybe further. Does that make sense? Another one, says I grew up in Kansas. Grain silos. If you've ever looked at them, most people claim they get bored driving through Kansas because there's nothing to look at. Well, you can watch for this. They have wire. I know that's in your way. Sorry. They have wires around them, but they're not evenly spaced. If you look closely, they kind of do that because it needs more reinforcement at the bottom. Because it's all the weight of the stuff inside creates a bigger pressure down here. The atmosphere does the same thing. That's chapter 14. There's air above us. It's a fluid, but it doesn't matter how much air, the volume, it's the height of it above us. So if these are like water molecules or air molecules, they're evenly spaced. But they do have mass, they do have weight, so when they settle, look at the spacing. Not my Band-Aid that just keeps coming off. Down here, they're smushed together because this spring has to hold back the weight of all of them above it, where this one only has to hold back the weight of these guys. That's why there's greater pressure with depth. Here's a barometer. Barometer measures pressure. I've closed it off so there's a balloon on here, but the balloon can flex. And it's connected to this side on your left. And if the pressure increases, let's see if I push on it. Yeah, it pushes that fluid down. You see that? So the pressure's greater over here when I push on it. Which raises this up. It's open to the atmosphere, so we just have air pushing down on it now on this side. Right now they're balanced because I put this on and there was air pressure in there. Same on both sides. You with me? If I pull on it, I can decrease the pressure on this side, increasing the space, the volume. I guess I'm trying to. No, forget it. This is what I'm trying to do anyway. This is why I got it. You know how it works? It's the difference between the two sides, like that tells us something. So, if I go down into a liquid, I hope it worked. Yeah. So there's greater pressure down here. How much more? The difference from there to there. That height. The pressure here, what's causing it? This much height of water, right? So how much water can that pressure hold up? Look, that much of water. Ideally, this height difference is the same depth that this is down. As I come back up, it's not as deep. You get the idea? Yeah.
Are we using mercury in that thing?
This is just blue water.
So if we use something else, wouldn't the difference be different?
Yes. Because pressure not only depends on the depth, but what material you're using, what fluid. The density of water determines the pressure. What if we replaced it with mercury? Greater density. It's heavier for the same space. So yeah, density is bigger. So if we replace this with mercury, the same height of water and the same height of mercury, who would create more pressure down here? Mercury, because it's denser.
So is this a standard apparatus for measuring pressure?
Yeah, this is a classic standard barometer. They're moving away from it because they're getting more digital and digital, but you probably, on doctors' walls, remember when they take your blood pressure? Sometimes they still have these on the wall and you can watch the thing go. They pump you up, increase the pressure, and you see it rise. Like that. And then as the pressure drops on the cuff. Or they have a needle. Sometimes your book describes an aneroid barometer. But they work under the same principle, a difference in pressure from the two sides. Let's do this one. Oh, somebody had a party. Okay, if I fill this full of water, I got 3 holes in the flask. I'm going to remove the holes, or the plugs, so the water can come out of the holes. Where will the pressure be the greatest? Good, at the bottom. So it's going to create, there's more pressure here, similar areas on the sides. So which one will have more force? Bottom. Who will come out faster? The bottom. That's all there is to that. Let's see if I overshoot. Comes out. Yep, further. And, yeah, a lot faster. See, it's shooting out. It's got more horizontal component. That one. It's projectile motion, but for fluids. There's still forces, there's still speeds, there's still projection. Then we make a mess. But yeah, there's still pressure down here. Now, see, the pressure's decreasing, and as it decreases, there's less pressure, less force, less speed, and it doesn't go as far. So, yeah, it's a good stopping point. Because I'm right to buoyant force. And we'll talk about Archimedes' principle and buoyant force. Unless you got any questions. So just remember the ratio. You got to consider both mass and volume. Pressure is depth dependent. Doesn't care about volume. But it also depends on what fluid you're using. If you replace fresh water with salt water, they have different densities. You're going to float differently. That's what we'll get into next time. Have a good week.